So today, rectifiability and tangents. So I'll motivate everything with the Euclidean case. So suppose that we have a subset of Euclidean space that's rectifiable, and has finite Hausdorff measure. Then Rademacher's theorem and some measure theory implies that E has an approximate tangent plane almost everywhere. So it implies the existence of an approximate tangent plane. Almost everywhere. Okay. So what I mean by this is the following. So there exists an n-dimensional subspace. Well, I guess affine subspace. V. That approximates my rectifiable set at X. Now, we just have to be slightly careful in how we formulate what it means to approximate, because we don't have any type of smoothness, and so we have to allow for throwing away some parts of the set that are not well approximated, and some places where the approximation may be. Because we don't have a manifold, we might have small holes in our set, and we have to allow for these differences. So one way of formulating this is the following. So there's this affine subspace such that for every radius, we can find a good subset of E. So there exists an ER that's contained in this ball in E, such that this set is large. So if we look at the measure of E without this good set, this goes to 0, and it should go to 0 at the correct rate, which is, because we're dealing with n-dimensional Hausdorff measure, this is R. Right, so they're saying that, I'll draw a picture in a moment describing all this. So she's saying that this set ER is very large inside this ball. And the second condition that we want is that ER is close to this affine subspace. So the way how we measure closeness is using the Hausdorff distance. So the Hausdorff distance between ER and V intersect VXR. This also goes to 0 at the right rate, and because these are distances, the right rate is R. Okay. Here's my picture. Here's the point X. Here's the scale R. I have an affine subspace V. Now the set ER, which is the big set, is going to be in green. So this is most of my rectifiable set, going like this, and most of it lies within an epsilon r neighbourhood of V, and conversely, V lies in an epsilon r neighbourhood of ER. Okay, but I may also have some other bits of V of E that I can't handle, right? So I may have E without ER, which can be some pieces like this, and maybe I can't approximate them very well, but they are small. And it's necessary to exclude this type of set, just because we are dealing with rectifiable sets, right? In the definition of rectifiability, we have countably many Lipschitz maps. So this could be some of these bits of noise floating around. We also have a set of Hausdorff measure 0. So there could be all sorts of noise floating around, but it has to be small. And that's what the first condition asks for. Okay. So the converse to this statement is also true, and it's, I think I gave it as an exercise in Attila's book. So the converse is true. So namely, if you have a set of finite Hausdorff measure, and at almost every point it has an approximate tangent plane, then the set is rectifiable. But this is not the most interesting result. Okay? So the converse is true, but it's not very useful. So a much better converse is given by the following theorem. So a much stronger converse. To Masterman in 61 and after that in 75. Right, and it says the following. So suppose that we have a subset of Euclidean space, finite Hausdorff measure, and also that it has positive lower density almost everywhere. So this quantity, which is the limiting of the measure of balls, is positive. So what's this condition saying? It's saying that at all scales you see an n-dimensional set. Right? There are not some scales where suddenly the set disappears and then later on it will reappear. So it says that at all scales you see some set. But that's kind of the dimensional assumptions. And now suppose that for almost every point and for every R, there exists an ER such that 1 and 2 holds. Right, then E is rectifiable. So, just to save you the pain, what's the difference between the converse? This there's the ER and VR such that 1 and 2 hold. So the difference being that V can depend on R, right? Whereas over there, V is fixed, right? Whereas now we have VR depending on R. So this tangent plane, the tangent, can depend on R. It can rotate. So it may be the case that at one scale we have our set, and we have its tangent that looks like this, and we have our set that's like this. But when we blow up even more, we may have a completely different tangent. And if we when we keep going, we get a completely different tangent again. Okay, so of course these are just the hypotheses are much weaker, but once we know that the set is rectifiable, then we have a unique tangent. So this picture can't happen, but the hypotheses allow for it to be, to be the case in order to prove rectifiability. And the fact that this much weaker hypothesis is essential for as an intermediate result in many results in geometric measure theory. So Marstrand and Matterley use this to prove something called the regularity of Hausdorff measure. So in the first lecture I mentioned this open question about whether sets with Hausdorff density 1 are rectifiable. Right? So the case, in Euclidean case, it's due to Marstrand and Matterley, and how they prove it is they first show that you have this type of tangent behavior. And this is also the starting point for Price's density theorem. So, and all of them crucially rely on the fact that these tangents are allowed to rotate as we zoom into the point. So, of course, now the question is, what about metric spaces? Well, first of all, we need a definition, right? So, if anyone has any experience in a metric space, there's a very natural conjecture to do here, which is, well, what if we just put Gromov-Hausdorff distance here rather than Hausdorff distance? And that's exactly what we can do. So just to be a bit more precise, so we need to formulate a question. So what does the question even mean? We don't have affine subspaces. There are no. Next, well, we can replace the Hausdorff distance by Gromov-Hausdorff. Distance. So roughly speaking, if we have two metric spaces, M1 and M2, the Gromov-Hausdorff distance between them is the infimum So the idea is we take two metric spaces, we isometrically embed them into some other metric space and look at the Hausdorff distance between the embeddings and infimize over this. So we look at the best possible way of trying to align these two metric spaces together in another metric space, and then we look at the Hausdorff distance. So the infima value amongst all metric spaces Z and isometric embeddings of M1 and M2 into Z of the Hausdorff distance between the two in Z. Right. So now we can ask for this type of condition. We do the same construction we're asking for this big set, but now we replace this Hausdorff distance by Gromov-Hausdorff distance, and we replace the affine subspace by just Rn. But we have to put a different norm. We don't know that the norm will be Euclidean. And yes. So Rademacher theorem can be used in almost an analogous way to that proof over there, to prove the corresponding statement for metric spaces. So let me try to give an idea of how you do this. So, and I'll try to give a bit more detail than what I did up there. So, using well, let's take Kirchheim and measure theory. So there's a problem. So if we have a rectifiable subset of a metric space with finite Hausdorff measure, then we can always find by Lipschitz reparameterizations of this. So then for every epsilon, there exists a decomposition of E. Well, maybe and another set. And the norms on Rn and 1 plus epsilon by Lipschitz maps Fi that go from EI into Rn with this norm. This is really just running. This comes straight out of the definition of what a derivative is. And so consequently, with a little bit more work, we can prove that these sets Gromov-Hausdorff converge to, I mean, on the scalings, that Gromov-Hausdorff converge to some type of limit of these norms. Right. In fact, we get a much stronger convergence than what Gromov-Hausdorff requires. Okay, so I'll just write down something more precisely. So then, consequently, for almost every point, right, we can find for almost every x, there exists a norm on Rn, and the sets from before, ER, contained in E intersect BXR, such that one holds, maybe I'll just write it down. And Gromov-Hausdorff distance of ER to Rn equal to this norm goes to 0. We actually get much stronger convergence than this. From these by Lipschitz maps, we get a much stronger convergence than Gromov-Hausdorff. But in particular, we get Gromov-Hausdorff, which is what we'll need for the converse. Right, and actually, there's a relationship between these two things. If you know what your tangent norms are, then that gives you what the by Lipschitz parameterizations are. Right. So, for example, if all of your tangent norms are Euclidean, then straight out of this, you know that you can always 1 plus epsilon by Lipschitz parameterized by Euclidean space. And conversely, if you can parameterize by Euclidean spaces, then you know that your tangents are Euclidean too. And you can replace Euclidean for any other particular norm. So now the converse question really becomes the converse to this. So now the question, does the converse hold? convergence.
So in the graph of distance, basically you don't know what is the ambient space where they are converging. So there, do you have really Hausdorff convergence in any scale space of X, or it is a jargon of Hausdorff and you don't control where it?
Well,
that there is kind of any. Right?
Yeah, you're right. So yes, but of course you of course can't really embed Rn into X.
Yeah.
But excluding that problem, yes, all the rescalings happen inside X. And in fact, they're even so. It's stronger than just Hausdorff because you have this Lipschitz map that takes you between the two of them. So it's more like it's really a uniform convergence down.
Yeah. Which I guess is a difficulty when you want to go on the in the direction because you don't control Z.
Exactly. Yeah. In fact, you just forget about Z basically. Yeah. Right. So now, just something. Well, actually, this is related to what Andrea was saying. Right, so the Gromov Hausdorff distance is invariant under isometries, right, just simply by definition. So that means that this notion of tangent is invariant under isometries of some remarks. So since Gromov Hausdorff distance is invariant under isometries, so is this notion of tangent space. So this converse question is actually it's closer to the Marston-Mattler theorem than this theorem, right? Than the easy converse that I didn't go through, but that I didn't really discuss. So because every time we allow these tangent spaces to rotate, well, of course they're all isometric to each other, right? So, and in fact, if you have a subset of Euclidean space, this converse question is equivalent to the Marston-Mattler theorem, right? So therefore, so compare to Marston-Mattler theorem, right? The rotating tangents are all isometric. In fact, if B is a subset of Euclidean space, the converse question is equivalent to the Marston-Mattler theorem. And so, yes, it's true that we do get the characterization through tangent. So I'll state the theorem now, and then basically for the rest of this hour and the next hour, I'll try to give a sketch of the proof. So the converse is true. Here's the theorem. So the same setup as what I mapped, we have E in X, finite Hausdorff measure, and positive lower density. So now, of course, well, there's quite a few converses that you could ask for. One is, do we have to pick a norm at every point? Or are we allowed the norms to vary? And indeed, we can allow the norms to vary. In fact, we can even push it a bit stronger. We can suppose that we have tangents that are by Lipschitz images of Rn. Okay. So suppose for almost every point there exists some constant. This will be the by Lipschitz constant of the tangent, right? And for every radius, there exists, again, we have the good set right, and I'll just put such that one holds. And a metric row on Rn that is k by Lipschitz to regular Rn and the Gromov-Hausdorff distance of ER to Rn with this metric. And we look at the unit ball, or the ball radius R. So this goes to 0 at the right rate.
So the metric below that depends on R?
Yeah. Oh, yeah. Then is rectifiable.
Is this case supposed to be like 1 plus epsilon or can
No, it can be anything you like, it can be rigid.
The assumptions about rank metrics is not so essential. Is it? Or is it much simpler to?
No, it's what came out of the proof. So, yeah. Of course, even the fact that this can be large is not that important, because if you want to just take norms, the square root of n is enough here, right? But it's just actually quite, you can really push this quite far. And in fact, for one dimension, you can push it even further. So, this is still to appear on archive at some point this year. So if n is 1, then the tangents can just have to be connected. Right? So it can replace with any connected metric space. Okay, are there any questions?
This lower density condition is necessary.
Sorry?
This lower density condition is necessary.
Yeah, it's necessary. It's even necessary in Euclidean space. Yeah. roughly speaking, if you don't have the lower density, then at that scale, kind of, you don't know anything about your set, and you can hide whatever you like at that scale, provided at some scale later, you know, fix it. Yeah, I guess a bit more precisely. Hausdorff, being Hausdorff close to something is determined just by finitely many points. Right? And so you can just, provided you put a lattice at your certain scale, then you satisfy the Hausdorff condition. But then you can hide lots of stuff. Okay, so the sketch will kind of go through this lecture and next lecture. So the starting point for the idea begins with a classical result of Reichenberg. So I'll recall the Reichenberg parametrization theorem. Same idea. Actually, just specify, I'm going to talk about the proof of the first theorem. Right. The idea begins with classical parametrization theorem. So it says the following. So if we have a subset of Euclidean space, and we have a stronger hypothesis than what I've discussed so far. All of the other characterizations involve infinitesimal tangential behavior. The Reichenberg theorem asks for uniform convergence to a tangent. Right. So if there exists, suppose that there exists some epsilon and r positive, such that for all scales below this r, there exists an affine plane. Such that the Hausdorff distance between E and V is at most epsilon times r. Oh, and probably epsilon should be less than 1. Then the conclusion of Reichenberg's theorem is that E is a bipolar image of Rn. Or the sphere. I guess of the sphere. Let's say that E is bounded.
So E is n-dimensional. How can it be
Yeah. Thank you.
of the whole sphere?
Yes.
Yes, bound. You will have a boundary and center. I think it's not sensible.
Yeah, so it's bounded, and at every point you have a good tangent, so you kind of have to wrap around to itself.
You still talking about the Hausdorff measure, because I mean, it's part of the body.
What did is a point.
So it could be just some other topological manifold. So it could be just some other smooth manifold. And it cannot be by it's not the local state.
It's just a local state.
Right, it's a local state.
Yes, okay, and now I can put R in. Well,
Sorry again, but what about connectivity, even local connectivity of E, according to this statement?
I think that's handled by the local condition.
And the asylum can be arbitrary.
Surely it has to be small.
So it's not just smaller than 1, it usually has to be sufficiently small.
Yes. Right, so the picture to have in mind here is of a snowflake. So let me draw you a snowflake. But here epsilon is going to be quite big, just for the purposes of the picture, but you can imagine flattening this quite a bit. And getting something better. I guess, yeah, okay, this is probably just meant to be a ball. So if we ask, right, in this statement we're not asking that epsilon goes to 0, right? Epsilon is fixed. So if epsilon were to go to 0, then the triangles would have to squash as we go down through the scales. We're not asking for that here. Epsilon is fixed. So if we ask for a smaller epsilon, the triangles would have to be smaller, but we would still obtain a snowflake at the end of it. Right? This is not by Lipschitz image of R. It's really necessary to have a bipolar image. Right? And the reason why is because in the approximations we get a multiplicative error as we descend through the scales. So you can imagine how one would try to prove this. You start off with the first scale. This is given by the approximation at this scale, right? So this is just simply using the tangent at unit scale, say. We get a map to, we can approximate our space. Then using the tangents at a smaller scale, we get new maps to R. We can build maps that go from this approximation to the next approximation down. This. So if each of these pieces are applying the hypothesis that we have at the next dyadic scale, we know that this space is roughly flat, this is roughly flat, this is roughly flat, and this is roughly flat. But the only way to piece them together is by going back downstairs. Right? So we can build maps that go like this. But by the nature of how the Hausdorff distance works here, we get a by Lipschitz error that goes from here to here. Right, so this map is 1 plus epsilon by Lipschitz, say. But this error only happens at the scale of 2 to the minus 1. And when we go again, we encounter another 1 plus epsilon by Lipschitz error. This again is another 1 plus epsilon by Lipschitz error. And so if you were to just compose them and naively estimate them, the by Lipschitz constant is now 1 plus epsilon squared, and this is bad because it will blow up as n goes to infinity. But the point is that this new error only happens at the scale of 2 to the minus 2. Right. If you were to go all the way from down here to up here, you don't get this accumulation of error, and this is exactly why you end up with a Holder map, or a bi-Holder map. Right, so we have accumulation, well, let's say the accumulation of multiplicative errors. So normally this is bad, right? This is scary, but it only happens at smaller scales. And it's exactly in the right rate for you to get a bi-Holder parametrization. Okay. So, what we want to try to do to prove this theorem, a natural first step is to try to do something like this, right? To try to get some type of Reifenberg type parameterization for our setting. So can let's try to get a Reifenberg type parameterization of E. Right. There's of course some big differences. Now, the first one is that we're in a metric space and we only have Gromov-Hausdorff estimates. E is a subset of a metric space. And we are considering Gromov-Hausdorff distance. This isn't such an issue. Well, it is certainly the least of the issues. Right. Another problem is that over there we allow the tangents to vary, right? And this isn't necessary. This is not just referring to the fact that those tangents are allowed to be by Lipschitz. Even if we allow them to be norms, right, that vary through the scales, then this would actually cause some technical problems that we'd have to fix. Right? So if the tangents can vary from point to point, and scale to scale. Right, so this is a more serious issue. But the real issue, the one that really requires something to overcome, is the fact that we don't have uniform convergence to tangents. Right?
Uniform with respect to x.
Yes. And I'll say a bit more about this in a second.
so you are now under this assumption, so under similar.
No, we're under those
Okay,
assumptions.
yes.
Yeah.
So you are not trying to prove the generalization of Reichenberg.
No, but it will come out of it.
Okay.
Yes, but no, we're under those assumptions. Yeah.
Can you say 2 words about the example before? So it's very convincing that it's why works and why is not Lipschitz, but why is not rectifiable? I agree it is not, but is there a clear way to see?
This snowflake will have dimension bigger than 1. Because it being a bifolder image, it will have some bigger dimension than 1.
Okay, this is okay, but is there a clear way to see it from what you say? So I disagree, but say from this fact that the scales don't go well, from the proof that I agree, it's not verifiable, but
I'm not sure I understand. In which
So
one?
basically, you said that this multiplicative errors breaks down the fact that one can observe a Lipschitz image.
Yeah.
Okay? But it is enough to have a bifolder image. Okay, I agree. And what prevents that to have rectifiability? Is there a way to see from there, or you're just two different?
So I guess probably there can be a rectifiable piece.
Mm-hmm.
I would not exclude the fact that it could have a rectifiable piece, but of course it would be a much lower dimension than the actual dimension of the snowflake. Right? So I guess you could have a
You throw away a 2 big set, basically.
Yeah. Yeah, it would be there will be a rectifiable piece possibly, but of the wrong dimension.
Okay.
Yeah, but because this can even be fractal dimension, right? So, but there could still be some rectifiable piece lying in it. Yeah.
Thanks.
Right. So before trying to go into some more details of this next time, I just want to get some kind of measure theoretic setup out of the way. So we have finite Hausdorff measure and positive lower density. So what these two conditions imply is that for small scales, the measure of a ball is comparable to the radius. If this is the most Cx RCn and bigger than for all r less than some Rx. So I'm just going to assume a uniform bound on this, right? So we can assume that the space is alpha regular. Right? So E is alpha regular. And also, by basically the same type of argument, we can suppose that K is uniformly bounded.
This is by splitting into countable pieces.
Yeah.
At a density point.
Exactly, yeah. Right. So now we come to this problem of uniform convergence. Right. So the fact that we don't have a uniform convergence to the tangent, we can still try to do some measure theory, and it gives us the following. Right. So tangent assumption. So it's the following. So it says that for almost every x, there exists a scale R such that all smaller scales, when I look at E intersect BXR, this is close to a tangent, right, to some Rn with a metric. That's by Lipschitz to Euclidean norm. But so I won't be precise by what I mean by close, I'll draw a picture instead. But then the point is that we can now filter by R of x. Right? We filter by R of x. So we get a subset G in E and some positive number R such that for all scales less than R and for all x in our good set, this scale where we see the good tangents is less than is bigger than R, right? So we know that at least below scale R we always have very good tangents for these points, right? And we can ask that the good set is as big as we like. So again, this is just by doing measure theory. And then finally, just to draw a picture on the next board, I'm just going to consider the case, well, I guess always we can scale so that R is equal to 1. And we just go through the case that n is equal to 2. But the idea is exactly the same. Yeah, it will be determined at the end. Yeah, so epsilon and what close enough means will be determined at the very end of the proof.
You fix it before you find this.
Yeah, yes.
Right.
So now I have to draw a picture. So this is the unit square. Maybe I'll make it a bit more square. So the fact that I have good tangents means that and let's fix x naught in G. So the fact that I have good tangents means that I have Gromov-Hausdorff approximations of a ball over here. Right? One way of formulating this is that I have bi-Lipschitz maps that go from here, say with the Euclidean norm, into x. So by good enough, I mean I can fix a lattice over here. And I can find bi-Lipschitz maps with, so there I have a uniform bound on K, but it's also to some rho, right? And rho is bi-Lipschitz to the Euclidean norm. So let me just say that this is a sigma bi-Lipschitz map into x for some sigma bigger than 1. That it will just come out of all the other parameters. Right? And what happens is it maps this lattice into a ball in a Lipschitz way. I think I have enough points. So this is what it means to have good enough tangents. Now, if we were in Reifenberg's assumption, in particular on the uniform convergence to tangents, we can iterate this. We would like to iterate this. So maybe I'll start there. So we want to iterate. So what I mean is, I now pick this point, which I know is in my metric space, because that's what it comes from the assumption. So let's pick this point x1, and now I want to use the fact that x1 has good tangents. So what that means is that I can then find my lattice point here, and map this over to here. And this is how one starts building a Reifenberg surface, right? The problem is that this only works if x1 is in G. We can only do this if x1 is in G, and it may not be. But because all we know is that right, we have Hausdorff distance between our model space, let's just say this is Rn, and ER. And ER is just a subset of E. But it may not intersect G. In fact, all of these points that we find may lie outside of G. So they are not good points, and we don't know what their tangents look like. In fact, the green points may not have tangents until we're down at a much, much smaller scale. Right? So we can't iterate. And this is the key difference between Reifenberg. For Reifenberg, when you look at this point, you know that it has a good tangent, so you can keep on going. But for us, x1 may lie outside of G. And in that case, we can't do anything. We have to stop. So if x1 is not in G, we simply stop. Right. If x1 is in G, we iterate. I'll go through more carefully next time what this means. But basically what happens is that then we can parameterize some of E using a Reifenberg type map. But what we have to take care of how often we stop. So this is a bad set. We have to show that this doesn't happen very often. Relate that to the fact that the complement of G is small. Right, to say that we don't stop very often. And then we have to do something to handle the fact that we've stopped. And of course, I haven't told you at all how we get back to rectifiability. Right. So next time, just to say it again, I'll do this construction carefully. Say what happens when we stop, how to fix something, and then finally we will be able to deduce rectifiability at the end. Okay. So thank you.